Good morning, everyone. Today we will start with structure realization of the IIR filters. Okay. So over here there are six types of structure realization process. First one is the direct form 1. In short, it is also regarded as DF1. Then we have direct form 2. So it is also regarded as DF2. Now this direct form 2, it is basically obtained by the rearrangement of the filter components or the filter designing which we do in DF1. So basically we do the rearrangement in the schematics to get DF form 2. Okay, DF2. Then next is cascade form. Then fourth is parallel form. Fifth one is transpose direct form, and last one is lattice structure form. We will not cover lattice structure form in our course. So, however, if you get a short note, uh, you should mention this name, lattice structure form. Okay. So we will be mainly concentrating on the first five: direct form 1, direct form 2, cascade form, parallel form, and transpose direct form. Okay. So starting with direct form 1, the difference equation of any given filter is given by yn equals to negative of summation of k equals to 1 to capital N ak y of n minus k plus summation of k equals to 0 to capital M bk x n minus k. So if you see over here, your ak, it varies from k equals to 1 to n, whereas bk, it varies from 0 to m. That means bk are the coefficients which gets multiplied with the input sequence. Okay. So from here, if we calculate the z transform and we take n equals to m equals to 2, then we get yz equals to minus of a1 z inverse yz minus of a2 z inverse yz plus b0 xz plus b1 z inverse xz plus b2 z to the power minus 2 xz. Okay. Now after rearranging over here, we get yz by xz, which is equal to h of z, is this equation b0 plus b1 z inverse plus b2 z to the power minus 2 divided by 1 plus a1 z inverse plus a2 z to the power minus 2. Over here we have taken n equals to m equals to 2 just for the sake of our convenience, so that we can design the filters in an easy way, and then from there you can understand. So if you want, we can you can just extend this series also. That's not a problem. Okay. But we need to understand how the architectures are being made. Okay. So if you look, this is your hz value. Now we have already discussed about how we can design the structure, we can realize the structures of the FIR filter. However, IR filter is slightly different. The reason being, apart from the present and the past inputs, over here the past outputs are also considered for the calculation of the output. Okay. Now how it is done? So see, we are having xz. Okay. Now this is the input. So then we will see that the input terminals over here in this equation are associated with b0, b1 and b2. Okay. So in the first term, b0 is getting multiplied with the input directly. So over here we will draw b0 it is getting multiplied with the xz, and then it is going to an adder. So we are having this adder over here. Then we can see that the input is delayed by 1 unit. So we will be delaying the unit, this input exit by 1 unit, and then that is being multiplied with the term b1. Over here it is getting multiplied by b1, and it is getting added up with b0 component. Okay, so see, it is going to the adder, and that is going and being added to b0 component. Okay, then similarly, as we go forward, we have input which has been delayed by 2 units. We have already delayed the input by 1 unit over here. Then in the next step, if we again put the delay, we will be getting the input post this delay as 2 units of delay, and that delayed input, it is getting multiplied with b2. So over here, see, it is getting multiplied with b2, and then it is getting added up with the previous two input components, right? So over here, see, so this input region we have implemented. Now if you have further exit components, input components which are getting added up, then below this b2 you'll have to add up those components to complete this input, what do you call, input and its delays getting multiplied with the filter coefficients, and then you can get this region. Okay, so let this region be A. Okay, now what we are left with? We are left with the components which are associated with these things. Okay, now if you look, this YZ this XZ component, it is getting added up with the other filter components, or the input output terms, with the other output terms, right? Now basically that will give you the this YZ, the output. Okay, so we will be giving this YZ, and then this output of this XZ, if you say this X dash Z over here, it is getting so these components, the input components, they are regarded as X dash Z, then it is getting added up with the other components. Okay, so this component over here where all the inputs have been accounted for, let's say it is X dash Z. Okay, so this X dash Z, it is getting added up with the other components to give you YZ. So X dash Z plus it is giving you the YZ. Now this YZ is getting delayed with by 1 unit, and it is getting multiplied with a negative of A1 over here, negative of A1 over here, and then it is getting added up with the X dash Z. Okay, so here is our X dash Z, so it is getting added up over here. Similarly, we have sorry, this should have been the Z to the minus 2. So A2 Z to the minus 2, it is being delayed by 2 units, and then it is also getting multiplied by minus of A2 unit, and then it is getting added up again over here. Okay, with the X dash Z and the this Z inverse Y Z component. Okay, so this is how this things are getting implemented. Okay, so over there you then get the addition of all these components, you get Y of Z. Okay, so this is the direct form 1 realization, direct form 1 realization. Now in the next case, where we have direct form 2 realization, what we say is that we have Hz which is given by Yz by Xz, right? Now we can write down in this fashion Yz by Wz multiplied by Wz by Xz. Okay, where Wz, it is equals to 1. Okay, So we can write that in this fashion. And if you remember, we have talked previously that suppose if I have hz and it is given by h1z multiplied by h2z. So consider this one yz by wz as h1z and wz by xz as h2z. Then we have said that it is having a commutative nature property. So we can write down hz is equal to h2z multiplied by h1z. Okay, in this fashion we have discussed. Okay, so what we can do over here, if you consider this one, this first one in the direct form 1, क्या हो रहा है? So this part, let's say this one is h1z and the next part as the h2z, then we can interchange this h2z and h1z and vice versa. Okay. Similarly, if you see in this case what we have done, we have just taken this and we have put over here. Okay, and this h1z, what I have done, I have put over here. Okay, for the sake of simplicity I have drawn it on the bottom just to show what I have done. Okay, otherwise this is the next step, first step, and the upper one is the second step. Okay, so if you see what I have done, I have taken the h2z and I have put prior to h1z and I have shifted h1z to the next level. Okay, or to the next step. Now over here, if you see carefully, what we are having z inverse terms which are lying beside each other. So in the direct form 2, what it says, let us combine these z inverse terms to get a composite equation or a composite structure. So in this case, if you see from here, when we go to here, what we have done, combining these two, I have just put one z inverse, and combining the next two, I have drawn only one z inverse. Okay, the rest of the thing, it remains the same. So what is happening over here? What is the advantage? If you look in the direct form 1, we were having 4 number of delays. Okay, whereas in the direct form 2, after we have completed this realization, we are having only 2 number of delays. Okay, so what is the advantage? The advantage is that the number of terms which has to be stored in the delay, it reduces significantly. Okay, so the number of registers to store the numerical components, it would reduce. And also, what is this delay? This delay is nothing but your numerical stuffs, right? Now this numerical stuffs, when you are reducing, you are basically reducing the mathematical complexity. You are reducing the mathematical complexity. Thereby reducing the computational burden. Okay. So when you talk of direct form 2, your computational burden, it reduces to a certain extent. Okay. Because what you are doing, you are reducing the number of the delays in the circuit, in the realization circuit. Okay. Then comes the parallel form realization. In the parallel form realization, you have band reject filter. Okay. So how you can implement the band reject filter? So if you look into this architecture, we can say the overall transfer function Hz is equal to H1Z plus of H2Z, right? Now, when you want to implement band reject filter, what happens? You have FC1, FC2. So this one is low pass filter, this one is high pass filter. So these are two different types of filters. So what happens? You have a signal component which you want to pass through this one. Say this is the FC1 is say 60 hertz and the FC2 is 80 hertz. Okay. Now what happens? You have a signal XZ, you pass through LPF, you get frequency components in the region of 0 to 60 hertz. Next, the same signal, it is being passed through high pass filter, and over here you get frequency components 80 hertz to infinity hertz, right? Now if you look into the band reject filter, you need both these components, okay, 0 to 60 hertz and 80 to infinity hertz. So in between 60 and 80 there will be no other frequency components, so you need both these components. So what you do, in the you add up the output of the low pass filter and the high pass filter, right, to get an output YZ. So this is what it has been done over here. If you see XZ, it goes to H1. Say for an example, the transfer function of low pass filter, it is given with H1Z, and the transfer function of high pass filter, it is given with H2Z. So by combining this low pass filter and the high pass filter, we can implement the band reject filter. Getting my point? We are able to implement the band reject filter. So this is parallel form realization. Why? Over here, if you see, the subsystem, this H1Z and H2Z, they are regarded as the subsystems. Now these subsystems, they have been arranged parallelly. Okay, that's why the name parallel form realization, it has been named. Okay. Next is cascade form realization. Here we design bandpass filter. Okay. Now if you look into the frequency component of the bandpass filter, FC1 and FC2. Now over here you have to remember that FL, that means the cutoff frequency of the low pass filter should be greater than the cutoff frequency of the high pass filter. In the first case, in the band reject filter, your FL should be less than FH. Okay, FL should be less than FH. Your low pass filter component should be lesser than the cutoff frequency of the high pass filter. That's why we were getting, so this is the low pass filter, its cutoff frequency, say FC1, it was lower than the FC2, which is the cutoff frequency of the high pass components, right? In the band pass filter, you have to remember, when you are designing the filter, you should have the low pass cutoff frequency should be higher than the high pass cutoff frequency. Okay, this should be clear in your mind. Okay, now once this is clear, you give XZ. Okay, now you pass through low pass filter component. So you get a component like this. Okay, now if you take the same signal and put it through high pass filter, and you get the output, and then if you add up, then what will happen? You will be getting a composite signal, something like this. Now if you see over here, all the frequency components are being admitted from 0 to infinity. That means what type of filter it is? It is an all pass filter. Okay, it is an all pass filter. So if your FL is greater than FH and you implement the filter in this parallel form, you get an all pass filter. So your total architecture, it changes. Okay, but we do not want the all pass filter. All pass filters have it has its own advantages. Okay, which we will not discuss over here. Okay, so we will restrict ourselves to the band pass filter. So under these circumstances, so what we need to do is that, suppose you have XZ, you pass it to H1Z, which is for the, say, LPF. So when we pass the signal initially to the low pass filter, we get a signal component like this. Next, if we pass the signal to the next component or the next subsystem, which is H2Z, which is an high pass filter, and its cutoff frequency is lower than the low pass filter. Okay, so what is happening? This high pass filter, it is cancelling out this region, this shaded region, and in the high pass region, this more than the cutoff of this low pass filter. These frequency components were already been rejected by the low pass filter, so there was no frequency component over there. So ultimately the frequency component what we get is this green shaded area. Are you getting my point? Now if you look into this green shaded area, it looks something like this, which is the frequency response of a band pass filter, and this is basically your YZ. Now in this case, again, just like in the parallel form realization, we are having two subsystems. Over here also we are having two subsystems. Now your YZ is given by sorry, not YZ, our HZ is given by H1Z multiplied by H2Z. Okay, now the next thing is that this multiplication is commutative in nature. That means H2Z multiplied by H1Z will give me the same results. Okay, so what do you mean by that? I mean, suppose I have filtered the signal using the high pass filter like this. Okay, now in the second stage I have applied the low pass filter. Okay, so in the first stage, when I applied high pass filter, this red shaded area, it was completely eliminated, right? In the second stage, when you are applying this high pass filter, the low pass filter, sorry, not the high pass filter. Herein we have applied the high pass filter first. So during the first stage, these low frequency components, they have been eliminated, and in the next step, when we have applied the low pass filter, the frequency components above the low pass cutoff frequency, they have been eliminated. So again, if you see, we are left with the green shaded area, which is again helping you to design the band pass filter. So when we talk about the development of band pass filter or band reject filter, in both the cases we have to use two subsystems H1Z and H2Z. However, the arrangement of H1Z and H2Z will be different. Okay, now coming to the realization form, how you want to realize this? You first implement H1Z and H2Z as per this form, direct form 1 or direct form 2, whatever you want to do, and then in cascade form you just multiply it you just implement the H1Z, the first filter, and then the output of this filter you give to the second one. Okay, so you get a composite output. Whereas in the in the first case, if you want to have this parallel form of realization, suppose you are given with Hz is equal to H1Z and plus H2Z, then what you have to do, you implement the filter H1 on the top, you implement the filter H2 on the bottom. Then if you see Xz, the same input is going to both the inputs. You just give the same inputs to both the subsystems, and the output of both the subsystems will be added up to give you the YZ. Okay. In the second case, in the case of multiplication, you implement the first filter. To that first filter you give the input, you get an output, you get the output and give it to the second subsystem, which will be acting as the input for the second subsystem, and then the output of the second subsystem will be your final output. Okay. Now the next type of realization is transposed direct form realization. So what is done over here, there are certain rules which you need to follow for designing or for the realization of the filter using the transposed direct form realization. The first one is the reverse the direction of signal flow. Second is interchange the input and the output. Third is reverse the roles of all nodes. And while you are reversing this role of all nodes, what happens is that your summing point, it becomes your branching point, and your branching point becomes the summing point. Okay. So let's see. let's say we are having a realized structure in the direct form 2 in this fashion. Okay. Now what we can do is that we can draw the signal flow, how the signal flows in the architecture in this fashion. Okay, so this is also called signal flow graph, because it is showing how the signal is flowing from input to output. Now what I have done, see, there is an adder, so I have put an adder over here. So this circular points, they are adder, and these arrows with some superscripts or subscripts, they are the multipliers. So what I have done, if you see, I have just taken this architecture and I have drawn its signal flow graph. So how the signal flows over here. Okay. Now, what our rule says, reverse the direction of the signal flow. So what I will do, and the second is the interchange the input and the output. So what I will do, first I will reverse the direction of the signal flow. So if you see, initially the signal was flowing in this way. Now I have changed the direction to the other way. Herein, the signal was flowing in this way. I have just changed the direction in the other direction. Okay. Similarly, in the YZ, we are having to the signal was moving towards YZ like this way, like this way. So I have just reversed the direction. Okay. Then what I have done, the next step is interchange the input and the output. This was my input, so I have changed to output. This was my output, I have changed to input. So just by doing these two, what I have done initially, if you see to this point, the signals were converging. Converging means they were being added up. So if you see over here in this parallel form, to a summer or to an adder, when the signal flows come, so they are converging to a point. That means addition is happening over there. Okay. On the other hand, when we are talking about this divergence means the same signal components, they move to different directions, two different directions. Okay. So what has happened over here, if you see the first one, initially this was the summing point, xz was coming, minus of a1 is coming, minus of a2 is coming, right? So this was the summing point. Okay. And if you see WZ node, the WZ node, it was the diverging point. The same signal was moving towards B0 and the same signal was moving towards the Z inverse delay components. Now what has happened? Their direction has changed. Since their direction has changed, the diverging point, it has become the summing point and vice versa. So summing points, when you reverse the roles of all the nodes, the summing points, it becomes the branching point, and the branching point, it becomes the summing point. Okay. So this is how you get this architecture. Then in the next step, what I have done, I have just rearranged xz and yz in such a way so that my xz is on the left hand side and my output yz is on the right hand side. Okay. So why I have done this? Because conventionally we put the input on the left hand side and the output in the right hand side. Okay. So this is how we implement the transpose direct form. Okay. So with this we complete the chapter IIR filters. If you have any question, please feel free to ask me. Do you guys have any question?
Sir,
Yeah.
hello. Sir, in parallel realization, is there any hard and fast rule that H1Z should be LPF and H2Z should be HPF or like that?
No. It can be in, the other way around also. I told you, no? See, if you are giving H1Z plus H2Z, okay, say in one instance, say it is 3, it is 4, it will give you 7. But if you change 4 plus 3, it is also 7. So if you change the nomenclature, doesn't matter. Are you getting my point?
Okay, sir.
Am I
So
clear?
for cascade form also.
Yeah. Cascade form also I told them it is having this commutative form. So H1Z multiplied by H2Z is equal to
H2Z into
H2Z
H1.
multiplied by H1Z. Okay. So 4 plus 3, 4 multiplied by 3, 12. 3 multiplied by 4, 12. Okay. So the output will not change. Now whether you take the first one as low pass filter or the second one as low pass filter, doesn't matter. But your logic
Okay,
should
sir.
be same. Uh, if you say that in the second case we have said the low pass cutoff should be greater than the cutoff of the high pass filter. If you do not keep this in mind, then what will happen? Remember, if we are not keeping this in mind, so what will happen? Low pass filter will be like this, high pass components are being rejected. In the second stage, you are having high pass filter. It is rejecting this component, so it is not there. Further, in the first step, there are no frequency components over here. So implementation of this filters will give you zero frequency. There will be no frequency components in the low pass and this thing. And what you will be having? You will be having something like what do you call? You will be having no frequency components. That means no signals will be there. No signal component will be there, because in the first step itself you have rejected all these components, na? So suppose it is 40 hertz. So from 40 to infinity you have already rejected in the first step. So there is no frequency component. In the next step, what you are doing? So that means 0 to 40 you have allowed. Okay. In the next step, what you are doing? Say it is 60. You are allowing 60 to infinity. It is lying in this region, 40 to infinity region. But you have already rejected this. So there will be nothing over here in the pass band. On the contrary, what will happen in the 0 to 40 hertz region, you have allowed the frequencies to pass through, but now in this case 0 to 60 it is in the rejection band, right? So in this rejection, since you are having 0 to 40 within the rejection band, in fact this 0 to 40 component will also be eliminated. Are you getting my point?
Yes, sir.
So you will be getting no signal. You will be getting no signal over here. And in the previous case, we have seen in the parallel, if you do not follow the rule, that means over there our rule was, in the first case our rule was FL should be lesser than FH. If you do not follow the rule, we get all pass filter, right? That means all the frequency components will be present. So you have to be very careful to design the filters. So this cascade form realization, or what I said now, no frequency components will be there. So it is called non-pass filter. No filter components is passed. All pass filter, non-pass filter. But this is not used. This has no advantages because all the frequency components will be getting eliminated. However, all pass filter, you can apply all pass filter, and what happens is that they are used to pass many frequency frequency components, and then you can try to make other types of filter. Say for example, if you have a low pass filter component, okay, now you want to get high pass filter high pass components, not filter. You get from this low pass filtered output, you try you want to get high pass components. How will you get? In the normalized form, we say 1 minus of low pass filter component will give you high pass filtered component, right? You must have studied in your undergrads. Am I right or wrong?
Yes, sir.
Yes, sir.
Right?
Yes, sir.
So what is 1? 1 is all pass filter component. The same signal, you have to use it. So all the frequency components will be present, minus the low pass filtered component, you will be getting the high pass filter component. So in this way, you are able to get what is there. You are able to use the all pass filter component for getting some legible outputs, right? So anything else?
No, sir.
Okay. Yeah, in some cases, numericals, I forgot to say. Say, for example, we give some partial fraction type of equation. So, h is equals to 1 by, say, s minus a multiplied by s minus a conjugate. Something, this type of equations were there, right? So, if I say that realize this in parallel form realization, so what you have to do, you have to convert it into, through partial fraction, you have to convert it s minus a plus 1 by b by s minus a conjugate term, or whatever the terms are there. So now you have got h1 and h2z, then you can go for z equals to h1z plus h2z. Okay. So for the implementation of the parallel form, you need to have addition. Okay. So I will be giving you implement this filter in either parallel form or in cascade form. So accordingly, you have to do the thing. If it is a cascade one, then what you have to do? 1 by s minus a multiplied by 1 by s minus s star. Okay. So now this is h1z, and the second one, it is the h2z. So you have to implement h1z and h2z separately, then you have to cascade it. Okay. Did you get my point?
Yes, sir.
Good. So if you have any question, I'll be happy to answer. Otherwise, we will just leave. Okay. If you guys do not have any other questions, we'll leave. Thank you.